Hi there. So it is week 13 and we are very close to the end of the semester. So hopefully you are hanging on in these last few weeks. I am sorry that I can't be there to give you this lecture in person, but thankfully the TAs will be very prepared to answer your questions, and I will be back in the office the next week. So Tuesday of Thanksgiving week, I will have office hours after my lecture to make up for this. Okay, so today assignment 7 is assigned. The instructions for assignment 7 are just like for assignment 6. So again, what you will do is building on the results from the error analysis you will have done for assignment 6, which is due today, you will do another iteration of error analysis for assignment 7. So these last assignments, they're all the same in some sense because I'm trying to encourage you to do several rounds of error analysis as you refine your feature space in preparation for turning in your project at the end of the semester. My goal is that you won't have any stress finishing up your project at the very end because you will have already done most of the work through the homework assignments that we will have. Okay, so today what we're going to talk about, we're going to revisit tuning with ensembles. You might remember we talked about that very briefly on this past Thursday, but we're going to go through that a little bit more slowly and clearly today. Then we're going to talk about co-training, which we didn't have time to get to last Thursday. Then we are going to talk more in detail about feature selection. So we have talked about feature selection a lot of different times throughout the semester, but now we're going to really explore the options. And then finally, we'll conclude this lecture with a discussion of discretization, which relates very closely to concepts from feature selection, and also time series transforms, which is another way of adding some features that kind of summarize over a series of instances that are temporally related to one another. So let's start with the example with ensembles and the tuning shortcut that I introduced last time. So again, we've been talking many times about the 3 stages of tuning. And I introduced the CV parameter selection meta classifier last time. And here we're going to use it to tune number of iterations for bagging and boosting. And what you'll see is that CV parameter selection goes through all 3 stages of tuning that we've talked about so far. So with just a brief recap, stage 1 is where you take the set of possible parameter settings that you're choosing from, and you evaluate each one of these choices through a cross-validation, and then you look at which one gives you the best cross-validation result, and you pick the parameter setting that gave you that best result. Then in stage 2, using that parameter setting, you build a model, and the training data is the whole cross-validation set. Then in stage 3, what you do is estimate the performance of that model. Not evaluate that model, but estimate its performance, how it would do on data that you haven't seen so far, through the stage 3 process, in which you go through stages 1 and 2 on each fold over just the training data for that fold. Okay, so here on this slide, you can see in the meta classifier folder, the CV parameter selection meta classifier. And you are very welcome to go ahead and use this CV parameter selection meta classifier in your project, where you will have to demonstrate that you know how to do tuning in your final project report. So I'm not going to require for the final project report that you manually step through the 3 stages the way we did on homework 4, or the way that you will in the second midterm, because by the time you turn in your project report, I will have already assessed your ability to do the tuning yourself, both through assignment 4 and through that second midterm. So I will allow you to use this shortcut. Okay, so if you're using CV parameter selection, you would select that on the classified tab, and you can see here the widget for that CV parameter selection. And you can see here that I have chosen the base classifier to be J48. And what you can see is that there are two command line parameters showing the confidence factor and minimum number of objects. Now, in order to go through the tuning process, what you have to do is select a parameter to tune and also set up the options for that. So here you can see how I would set up a tuning experiment where I would be tuning the confidence factor, and the minimum value would be 0.1, the maximum value would be 0.8, and I would go through 8 different levels. So I will end up choosing from between 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, and 0.8. Now, when I click Start to run the cross-validation experiment, it's going to go through the 3 stages of tuning. It's going to display to you what parameter options it chose in stage 1. Below that, it's going to show you the model that it built in stage 2. And finally, it's going to give you the stage 3 estimate. So now I'm going to step you through the promised experiment with ensemble methods. So I'm going to compare bagging, boosting, and stacking. And I'm going to do it on the labor negotiations dataset, which is one of the standard WECA datasets. So here you can see on the Classified tab, I have chosen CV parameter selection. And I'm setting it up to use bagging as the meta classifier. So you can see here that bagging is in the classifier choosing area. And I'm setting up to tune number of iterations. Inside of the bagging widget, I am going to choose as my base classifier J48. And you can see here that the parameter setting that's showing is -U, and there's nothing after that, and then -M2. Now, you see -U instead of -C.25 because in this case, what I have done, because it's bagging and I want to use the most unstable version of J48, I am turning pruning off. So -U means unpruned true. So now I'm going to run this experiment, and it's giving me the result of 85.9% accuracy, 68 kappa. And you can see, if you scroll up, that the value chosen for -I, the number of iterations, is 50. So it got the best performance when it had 50 bags. We were starting with 10 as the lowest, 100 as highest, and with 10 steps. So the middle one was the one that it chose as best. So I can also run a similar experiment where I am using boosting instead of bagging. So I would do CV parameter selection, and the classifier I would pick is boosting. I could still tune number of iterations, just like I did for bagging. This time, what I'm going to do is choose, so whereas for bagging, I chose a more complex, less simplified, less pruned version of J48. For boosting, instead, I take the opposite approach. I take the ultra simple version. So decision stump is like the simplest possible decision tree with only one node. So on every iteration, I'm adding basically one node to the tree. So, okay, so you can see here, so I've picked CV parameter selection. I chose A to boost. My base classifier is decision stump, and I'm going to tune the number of iterations with the same set of choices that I had for bagging. So I run it, and actually you can see it does better both in terms of percent correct and kappa. And let's look at what was the number of iterations that it chose. So you can see it was choosing from the same set of options that it had for bagging, but it chose as its optimal setting 20. Okay, so, and then I can compare these with stacking. Now, in this particular case, there isn't a relevant number of iterations. So I'm just going to build a classifier where I have 3 different base classifiers. So I'm going to go with SMO with different exponents. You can't see the exponent in this list, but I went through with exponent 1, exponent 2, and exponent 3. And I'm going to combine the predictions using naive Bayes as my simple top-level classifier. And here you can see it does just about the same as boosting did, actually. Okay, so now you have seen an experiment where I've compared across bagging, boosting, and stacking. And for bagging and boosting, I tuned the number of iterations using CV parameter selection. Okay, now we're going to move on to code training. We started to talk about semi-supervised learning on Thursday. And I mentioned that it builds a lot on concepts from clustering. And I reviewed EM clustering because in EM clustering, we are assigning every instance to every cluster probabilistically. And we start with the random assignment of every instance to some number of clusters that we pick. And then we iterate between holding one distribution constant and estimating the other, where the 2 distributions I'm talking about are, one is the association between instances and clusters, and the other is within clusters, the distribution of feature values. And so we can compute the association between instances and clusters based on how good relative fit is across the different clusters based on their distribution of features. And then we can take the cluster membership that we have computed this way and use it to compute the contribution of the feature values from each instance to the distribution of features within each cluster based on the weight assigned to an instance from the amount of membership that instance has in the cluster. And as we iterate, the clusters get tighter and tighter in a similar fashion to how they do in k-means. Now, we have stepped through this closely using pictures in previous lectures, so I'm really just reminding you of this concept, and you should go back and review if you don't remember. Now, when we were talking about plain and simple semi-supervised learning, the simplest version that I introduced last time is called self-training, and there it's very similar to clustering, except instead of starting with the random assignment of instances to clusters, we use an originally trained model from a small amount of data to build a model. We use that model to assign probabilistically an association between each instance and each class value. And now we have, for every class value, a cluster, and rather than random assignment, we have a much more systematic assignment that's in line with the class values that you want. And then you iterate in the EM fashion, and what ends up happening is that you get simpler clusters. So it removes the tendency to overfit that you would get from training on a small amount of data. Essentially, those complex cases that would have been learned and not distinguished from, simpler cases that happen more frequently when you train on a small amount of data, you would just remove them. So I think that didn't sound very clear. Let me say that in a clearer way. The idea is that when you train on a small amount of data, it's hard for an algorithm to tell the difference between things that happen very infrequently and things that happen very frequently. All else being equal, if you can get the same performance by basing a model on patterns within your data that happen more frequently or patterns in your data that happen less frequently, the model that's based on patterns that happen more frequently are much more likely to generalize to your test data. When you use EM clustering, your cluster definitions become based on feature patterns that happen more and more and more frequently as each iteration happens, because you will tend to redefine clusters in terms of ways that the instances fit best to the clusters that you have. So increasing the fit is like increasing the generalizability of your model. It's removing those things that are attached to patterns that don't happen very frequently. Okay, so co-training is a form of semi-supervised learning. It builds on all of the same concepts, and it is similarly focused on avoiding overfitting to a small amount of labeled data by leveraging a lot of unlabeled data. What's different about co-training and the simplest approach that we introduced last time is that you have two competing representations. So what you really want are two feature spaces that would divide your instances into very different neighborhoods. Because what that means is that if you have labeled data across your space, then in one feature space, you would some of those instances are more central to certain neighborhoods, and then in a different feature space, you have instances that are central to very other neighborhoods. So therefore, the number of instances that are central is likely to be larger when you have, two different views where each view is a set of neighborhoods defined by a set of features. And so having some labeled instances that are central to particular neighborhoods gives the ability to an instance-based classifier to assign an accurate value to things that are close to it. The more an instance is close to the center of a neighborhood, the more instances within the neighborhood that it will be able to influence. And so what happens is that if you strategically pick subsets of features that have the property that they define very different neighborhoods, then that means that you can reach, with a correct classification, or at least influence from your labeled examples, more other instances. So that's what you're trying to do. But let's step through that much more slowly. So what will happen is that you have a few labeled examples, but you have two very different feature spaces. And so what you can do is train with the same labeled examples two different models, one based on the first set of features and one based on the second set of features. Then you will use each of these models to label all of your unlabeled data. And for each one of your feature spaces, you are going to take the example most confidently labeled. So of the unlabeled examples, you will take the example most confidently labeled so let's say it's a binary classification problem. The one that's most confidently labeled negative and the one that's most confidently labeled positive, and you'll add them to your labeled data. Now, what will happen is that because your different feature spaces have very different neighborhoods, then when you look for the instances most confidently labeled positive and most confidently labeled negative, there'll be different instances. So what happens is that you can be very selective about which predictions you believe from your automatically labeled data. And you are going to get a different selection from the two different models. What that means is that the instances that one model labels very confidently are most likely labeled very unconfidently and possibly incorrectly by the other model. So whereas if you were doing semi-supervised learning with only one representation, you would probably get some instances right and some instances wrong. And that's going to be true anyway. But when you have co-training, the alternative models will be right and wrong on different examples. But okay, so in the ideal world, you would be able to distinguish which ones are they getting right and which ones are they getting wrong, and then you would just take the ones that one got right and the ones that the other one got right. Well, you're not going to know a priori across the entire data set which one to believe, but if you take those that are most confidently classified, they're probably most likely to be correct. So now what you have is 4 new examples, and you're going to train with both feature spaces over the expanded set. So for both of your feature spaces, some of the examples you added were ones that it would have been confident about anyway, but the other ones that you added because of the other feature space are ones it wouldn't have been able to get correct. And so this allows you to add in an unsupervised fashion instances to the training data that wouldn't have been reachable with only one feature space. But the key point is that you have to pick feature spaces that would define very different neighborhoods, because if you don't, then you wouldn't have this property that the alternate models have different unlabeled instances within their feasible reach. So co-training will be better than just a simple EM, or, which is basically the self-training approach, if the data that you're working with can be associated with 2 very different feature spaces that would define very different neighborhoods. And so what's creative in the application of co-training is the design of those very different feature spaces. So whereas in theoretical machine learning, the concept of co-training was designed, and there are many aspects of the algorithm and how it works that could be refined by people who make basic contributions to that core area of research. But as people who do work in applied machine learning, there's plenty of space for you to be creative as well, because you are actively working to create new feature spaces. And in fact, you're working now, even as you're doing an iteration over your feature spaces with error analyses over these last several homework assignments of the semester, you're engaging in that process. And so you could think to yourself, okay, what are those very different approaches to feature space design that I could be playing around with, especially as I'm trying to shore up weaknesses in my existing feature space by designing new, more nuanced features? Are there very different creative angles I could take? And would those very different creative angles possibly define, possibly cause my data to cluster in different ways? And therefore, would I know that I was getting very different neighborhoods? And then if I get very different neighborhoods, then maybe something like co-training would actually help if I have access to a large amount of unlabeled data that I could use to augment my learning. Okay, so there are tweaks on co-training, and co-EM is an approach that is one of those tweaks. It combines co-training with expectation maximization, basically EM clustering that we've been talking about. And the idea here is that that rather than kind of adding one pair of examples from each model on each iteration, what you're basically doing is you do one round of self-training with one feature space and then one round of self-training with another feature space, and you iterate. Okay, so as I was saying, what is it that makes good applied machine learning work in the co-training space? And that is determining what could be good alternative views on your data. So you may actually be able to identify subsets of your features that you already have that have the property that they would define very different neighborhoods. And so then that would be another way of going about trying out the idea of co-training with your data, even apart from adding new features. So from a very qualitative perspective, you could think, what makes sense in terms of alternative views based on kinds of features. So let's say you had a prediction task, you were trying to assign vacation possibilities to quality categories. Would people like this vacation or not? And so some features of a vacation might be ones that help you to determine how exciting that experience would be. And others might be related to how relaxing it would be. So exciting might have to do with, what kind of a challenge sport opportunities are there. It might be like, how far away from your home is it? How foreign is the culture to where you're from, and relaxing might be, does the bedroom have a very nice, comfortable bed? Is there a pool? How crowded is it, et cetera, et cetera. Movie reviews have a couple of different views. You've got the text of the review, and you also have metadata about the review, and also metadata about the movie that could be combined in there. And possibly those would combine together to create, so the metadata combined might create one view of neighborhoods within your review space, whereas the text might create another. Some representational differences that have been used in sort of paradigm examples of co-training: web page author prediction. Is it a faculty or student page? And so one representation might be the text on the actual page, and the other might be the text on the pages that are linked. Similar to the vacation quality, it might be how much did you enjoy a meal at a restaurant, and you could have features that are related to the ambiance or features that are related to the food. So you probably have better examples than this. This is really just to get your creative juices flowing. Now, co-training, like all forms of semi-supervised learning, would require a substantial amount of effort from you because it isn't built into WECA. So if you wanted to be able to do this, you would have to go through the iterations more or less manually, unless you could write code. So that's going to make it so that it's not very straightforward for you if you are not a programmer. So if you wanted to try any form of semi-supervised learning and you're not a programmer, probably your easiest bet would be to go for self-training because it's relatively easy to do even if you can't write code. And you should probably come to office hours and just talk it through with me, and I would be happy to help you figure out how to go ahead and do that in some simple way. Okay, so let's move into feature selection now. So why is feature selection important in the first place? We've briefly talked about various reasons why you would use feature selection throughout the semester, and you may feel like you already have a really good grasp on that, but I just want to review some of those. So one thing is to think about why it is that leaving irrelevant features in your feature space might hurt your performance. So I'd like to actually take this opportunity to remind you that when you do an error analysis and you identify that there's a feature that's actually confusing your model, I have said many times, don't fix that problem by removing that feature. So those are not the features I'm referring to when I say irrelevant features. I'm more talking about features that they probably are not helping to make a useful prediction in very many cases, which is true of the features that actually confuse the model based on the definition that we've been using when we talk about error analysis. Instead, these are usually pretty weak features, and they're noisy, and they're not that helpful anyway, and they're in our feature space. And so what is the problem with these features? Well, so let's say you were training just a simple weight-based model, linear. These are the features that would probably get very low weight. So they aren't going to probably cause that much of a problem there. But let's say instead you were using a decision tree learning approach. There, these kind of irrelevant features could actually hurt your performance. Because as you're adding nodes progressively to your tree, the deeper into the tree you get, the little and little and little data that you're actually looking at to rank your features in terms of information gain. And so as you move down the tree, it's harder and harder to distinguish those features that give you substantial leverage from those that just happen to look good because of the small number of instances that you're looking at. So if you want to carry your tree building down relatively far, then it's likely that these irrelevant features you left in are going to cause errors. Now, naive Bayes doesn't have that problem. So every time you compute a conditional probability, actually, you are using all of the instances of a particular class value. However, what it does have as a problem is that that every conditional probability gets multiplied into the likelihood formula. And so there's no sense in which some of those conditional probabilities are weighted less. And so if you have a noisy feature and you just have a couple, it's probably not a big deal because these irrelevant features probably have very, lukewarm predictions. They're sort of, not giving a strong push in one direction or another anyway. However, if you have a lot of these, then eventually the little bit of noise that each one adds in kind of overwhelms the signal. And so it's a problem if you have a lot of these noisy features. In SVM, probably the performance doesn't get harmed from having added noisy features, assuming that you have enough data to train on. But what happens is that the more features you have, the longer it takes to train. And so having a lot of them can just hurt in terms of time complexity. So feature selection addresses all of these problems. It removes irrelevant features so that you can train efficiently and so that you can train, say, a tree further without as much danger that you will introduce errors. And there are two main paradigms for feature selection that we'll talk about. One that's called the wrapper method and one that's called the filter method. So the wrapper method is the method that uses a classifier of some kind, which could be a very simple classifier, but what it actually does is it evaluates subsets of features. So in the limit, if we were doing an exhaustive search, it would have to evaluate how good each subset of features is out of your entire set, which would take a very long time. So if you're using the wrapper method, you also have to pick a search method so that you can search the space of subsets of features and only evaluate some. But you never just evaluate single features out of the context of a subset. You always evaluate a subset of features, and whichever subset is best out of the subsets that you evaluate, that's the subset of features that you would retain, and you would throw away all of the other features. In the filter method, it's different, and filter method is what we've talked about so far and what is used by default inside of LightSide, and also the one that I suggested that you use inside of Weka. What happens here is that every feature is evaluated using some criterion, which is usually related to the correlation that each feature has with your class value. And then the features are ranked and you retain the top N. Okay, so you have already seen these, the attribute selected classifier that we have used so far. And when we did, we selected as the evaluator, we used the chi-squared attribute eval. That's like essentially computing a correlation between each feature and your class value. And then we picked a ranker as our search method because for the a chi-squared attribute eval, it's meant to be used as an evaluation of each single feature by itself. And so ranker is what takes the metric that's computed for each feature, it ranks the features, and then you tell Ranker what n is, and it keeps the top n. But you can use these widgets to do a whole variety of wrapper and filter methods. So we're going to step through what those options look like. Okay, so first before we get into that whole space of choices, let's talk about the idea of evaluating feature goodness, kind of a little bit more abstractly. So there are approaches to feature selection that don't necessarily fit the paradigm of, I'm evaluating subsets, and then I'm going to look at how these subsets are good relative to one another. Another possible way to do feature selection is just out of the whole set of features that I have, what is the smallest subset I can pick that allows me to distinguish each of my training instances from each other. So, for example, if I have one feature that has a unique value for every instance, then I could just keep that one. But actually, that wouldn't be a very useful feature to have. But let's say that I have 3 different features, and each one has 10 different values, and but 2 of those features it has a unique combination for each one of my instances, then I don't need the 3rd feature. So, so the idea here is that I never have to look at my class value in order to identify this small subset. I'm not actually looking for the features directly that are most predictive. All I'm doing is I want to have options that could pick out every single instance, because what that means is that those features could actually be used to train any model, because I could, with the features I have, identify any subset of instances and distinguish that subset from all the other instances. So whatever binary classification task over my instances I want to do, I could learn it with those features. So that would be a good way of narrowing down. Another possibility is that I could just take an algorithm like decision tree learning, and I could train a tree, and I could even turn off pruning and grow out the biggest tree. And then I could say, I'm just going to keep all of the features that were part of my tree and throw every other feature away. Now, this tree that I built might overfit to some extent, but I will have, by building it, thrown away a bunch of my features. Now I have a subset that can train a pretty good model, and I really just want to simplify it a bit. I don't want to overfit so much. So now if I use that subset and I train with a different learning algorithm, I can be a little bit more conservative. So I'll end up with a simpler model, and I'm very likely to find a good model within this set of features that I had, because I already built a pretty good model, possibly overfit, with that subset of features. So some of our metrics, like chi-squared attribute eval, are like very simple classifiers. So 1R, that's a rule learning algorithm that can only use one feature to build its model. You could imagine that you could build a 1R model with every single one of your features, and then you could evaluate that model's performance. So now every one of your models, they have the performance. That's the highest accuracy you can get with each one of those features by itself. And now you could rank those and pick the subset that were better than the rest. And essentially, that's using the filter method. So it's most efficient to use this filter method, where you assign a metric to each feature, you rank, and then you keep the top n. But the problem is that in thinking of each of these features by themselves, what you don't factor in is that some of the features are really only valuable in combination with other features. So And you will never be able to detect that value when you're just evaluating each feature by itself. Whereas if you were evaluating a subset of features, then as long as that subset includes a feature and the other features it needs in order to be valuable, then you can see its value because you see it in that context. So subsets allow you to identify the value of features where that value can only be seen in combination with other features, assuming that when you evaluate the subset, you allow the features to combine with some nonlinear modeling approach. So if you want to look for an optimal subset, you need to have a good search method. We've talked already up until this point about how we characterize the non-exhaustive search methods of all of the algorithms that we're using as greedy methods to some extent. And so the greediest method for doing subset-based search for a subset of features is called a best first search algorithm. Now, there are two different best first search approaches. There's a forward selection approach and a backwards elimination approach. Well, there's also a bidirectional version of it, but we are just really going to focus on the two simple ones, the forward selection and the backwards elimination. Forward selection, you start with nothing and progressively add one feature at a time, each time adding the one feature that gives the biggest boost to performance. Backwards elimination, you start with the whole set and you prune away features such that you're removing features that don't harm performance of the remaining subset or harm it as little as possible. So let's step through forward selection first. So let's say that this set of blue boxes is your starting feature space. Now, they're all light blue, so that means you haven't selected anything yet. So now what you're going to do is test each one of these features. And you're going to see which feature, a singleton subset, is the best performing one. And then you will pick that subset, which is, as I said, a singleton subset. So now we want to see, okay, I want to expand this subset out. So I'm going to evaluate all possible subsets that include the subset I already have. So I'm going to step through all of the remaining light blue squares and see how good is the subset that includes the tested new feature alongside the ones that we have already picked. And so then I will add that. And now I will have a subset that includes two features. Now I can see, okay, I still have n minus 2 light blue squares left. And now I'm going to step through each one of those n minus 2 light blue squares and see, of the ones that are left, which one, when I add it to the two I've already selected, gives me the best subset. And then I add that one. Okay, so that if I was just going one by one, the way you just observed, I would be doing forward selection, and eventually I would stop when I cease to get substantial improvement by adding an additional feature. In backwards elimination, you'll see I start with the default is I select everything that I have. So everything here is dark blue. And now what I'm going to do is look through all of my dark blue squares and see which one can I remove and have a subset of features that's just as good as what I started with. So if I remove one, now I have a subset that's n minus 1. I could make an even smaller subset by removing one more feature. So of the n minus 1 that I still have, I'm going to see for, which of these can I remove and have the smallest negative impact or no negative impact, or really even positive impact if some of my features are causing me to overfit by removing. So then I remove another one, and I could potentially remove another one, and I will keep doing this until it doesn't help anymore, where it starts to really hurt. Now, that was best first. So each time I added or removed one, but I could look for the top 3 options, the top 4 options, the top 5 options, and then branch out. And so then, like, let's say I picked 3 possibilities. Now I have 3 different subsets of features. And for each of those subsets, I look for, 3, I look for which one would I add to that subset. And now I can branch 3 more. So now, after I branched and I got 3 possible, let's say, possible worlds, each one of those then I move forward from, and there could potentially be another 3 that I would look at. But then I would have 9. And if I just want my beam to be 3, of the 9 possibilities, I would pick the top 3 and throw the others away. And so then I can branch and then bound, branch and then bound. So that would be the end best tweak on all of this. So I don't have to just commit to the one choice that's best. I can keep some options around and then look at how I could build from each of those options moving forward into the search space. Now, different of these approaches will make different mistakes. So we've talked, and when I say different approaches, I mean forward selection versus backwards elimination. Backwards elimination will produce larger subsets of features. And oftentimes, it's going to perform better in the sense that it has less of a danger that you're going to throw away something important that you actually need, which means it's more likely to include all of the features that you need in order to build your optimal model. However, it's less efficient because you will end up possibly leaving in some features that you don't really need. Forward selection is really good at removing redundant features. You're going to get a very lean feature space out of forward selection. And it's going to be really good for naive Bayes because it's really good at throwing away those noisy, irrelevant features that would harm naive Bayes more than probably lots of these other approaches. It's also better for understandability of your model because it keeps the model lean, but it might throw away something hastily that would have been useful to you. Throwing away because it never got to the place where it saw that it should add it. Okay, so how do you navigate the space of possible feature selection techniques? So you'll see that there's a whole list of these ways of evaluating features, some of which are meant for subsets and some of which are meant for individual features. So CFS subset eval is a subset-based approach. It's looking for a subset of features that are highly correlated with your predicted class, but have low intercorrelation with each other. Classifier subset eval also looks for a subset of features, and what it's going to do is use some classification method that you pick out as a method for comparing subsets. So let's say you pick SVM as your comparative classifier. What it will do for every subset of features is train an SVM model and then look at how well that model performs on some held out data, and that will be the performance value that is associated with that subset of features, and you'll pick the subset that performed best. And with classifier subset eval, you get to decide which classification algorithm you're going to use. So consistency subset eval is going to look for a subset of features that gives you neighborhoods that are very homogeneous with respect to class value. So if you were going to use instance-based learning, consistency subset eval makes sense as a feature selection technique because you'll get neighborhoods that will have high utility for making predictions. SVM attribute eval is a beam search technique. It is using SVM it's like classifier subset eval, but using specifically SVM and specifically backwards elimination. Wrapper subset eval is essentially just classifier subset eval renamed. And okay, so all the ones we've talked about so far were for subsets of features. And now we have some that are for filter methods. So chi-squared attribute eval is the one that we have used in the past. and it evaluates the worth of each feature by computing the chi-squared statistic, which, as I said, is very much related to the correlation between a feature and the class value. So correlation attribute eval is another one that is very analogous in terms of its performance. Gain ratio attribute eval is like chi-squared but uses gain ratio. Info gain attribute eval again, but uses information gain. 1R attribute eval, again, the same, but uses the accuracy of a rule that has only that one feature as the metric. Relief attribute eval is very much, so now we're back to a subset evaluation approach. And it's very much like the consistency attribute eval. And then symmetrical uncertainty, it is very much like information gain, 1R, etc. Now we're back to like filter method approaches, and but it uses a metric called symmetrical uncertainty. Now, of all of these metrics that are assigned to single features, they will all have a very high correlation with one another. There's no a priori reason why one should be better than another. Really, in any random case, one or the other will be better, but it's not because it's systematically better per se, but just because it happened to fit that data best. So this is the kind of thing that you can play around with. Okay, so that's feature selection, and now let's move on to discretization and time series transforms. So discretization is a process that applies to numeric attributes. A numeric attribute gives you a continuous range. This so right now, this blue rectangle that you see is not a set of features, but it's a range. So at one end you have low values of the range, and at the other end you have high values of the range. So what you do when you discretize a numeric parameter is that you insert a boundary somewhere on the range, and then you create nominal attributes values for a nominal attribute where every instance that would have had a number that was in the part of the range that is before the break will get the nominal value that is assigned to that side, and everything on the other side will get the rest. So here you see a split was introduced halfway across. So then let's say there are two values, A, which is on the left, and B, which is on the right. So any value from the leftmost end up to that boundary will get value A, and everything else will get value B. So with one split, you get one nominal attribute with two values. But you could think of it as two binary values, one that's A versus everything else, and the other one that's B versus everything else. Now, if you add another split, it could similarly be one nominal attribute with three values or three binary attributes. Therefore, every time you insert a split, you could think of it in a way as being analogous to a forward selection feature selection approach where you're selecting from binary attributes. You could remove boundaries and aggregate across your nominal values, and in so doing, it's like a backwards elimination feature selection. And both of those would be supervised forms of discretization. So you would use reference to your class value to pick out places to insert those breaks that would improve your performance. But there are also unsupervised forms of discretization. One is called equal interval binning. And there, what you will do is take your range and divide it into intervals that are the same size from the standpoint of how you're interpreting them. So for temperature, for example, if you put in a break every 10 degrees, that would be an example of equal interval binning. Or for weight, if you put in breaks every 5 pounds. But equal frequency binning is different. What you would do is you would decide where the breaks would be in such a way that you have about an equal number of instances within each subset that has a particular value. So let's say it's temperature and half of your instances are below 70 degrees Fahrenheit and the other set of instances are 70 degrees Fahrenheit or above. Then if equal frequency binning in 2 bins, you could break at 70 degrees Fahrenheit and you would have 2 values, one of which represented less than 70 degrees Fahrenheit and the other everything else. Now, there's no reason why 70 degrees Fahrenheit is a particularly meaningful place on a temperature range. But the reason why you would have picked it if you were doing equal frequency binning is just because then you would get roughly half of your data on one side and half on the other side. Now, if you take equal interval binning, when you look at your trained model, it will make more sense to you because, say, you have breaks every 10 degrees, and so, each bin represents the same amount of degrees. But the problem is that data usually isn't spread so evenly across these ranges, and so what will happen is that some of your values will have very few instances, and so that creates problems when you're trying to build your model because you can't estimate conditional probabilities or weights very effectively when you don't have very many examples. So equal frequency binning is better in some sense for building a model outside of having any knowledge of where strategic breaks would be for getting good accuracy. Since you don't have that option if you're doing an unsupervised approach, then your best bet is to go with what's going to give you more data so at least you don't have sparsity problems. Okay, so for supervised splitting, then again, you can use an approach that's like forward selection or backwards elimination. So you can think very analogously to the feature selection approach. There are ones that are based on accuracy. There are ones that are based on information theory. There are lots of different approaches to doing this supervised method. Now, supervised discretization is built into some of our classifiers already. So naive Bayes, for example, and here it makes a lot of sense. If we have numeric parameters for naive Bayes, we know that one assumption naive Bayes makes is that the values for every numeric attribute within a subset for the same class value are normally distributed. If the set of values you have in your data is not normally distributed, then the conditional probabilities that can get computed are going to be wrong because it uses the fit parameters from the normal distribution. It fits to that set of values in computing the conditional probabilities. So those are going to be bogus if the distribution wasn't normal to begin with. So if you use supervised discretization, what you do is that you turn your numeric parameters into nominal ones. And now that you have a nominal attribute, you can compute conditional probabilities using the method that's applied to nominal attributes. And then you're no longer making that normal assumption. And so in that case, you work around that problem with the conditional probabilities. So earlier in the semester, we talked about using that normal distribution to compute conditional probabilities from numeric attributes, and we introduced the speaker ID data set, and we said that using regular naive Bayes was bad for performance because it made this assumption of normality which was violated in that data set. So at that time, we introduced one possible fix for that. But here, a fix would be to use supervised discretization. And there you can see we also get a substantial improvement in accuracy when we do that. Okay, so if you want to do discretization in Weka, you can use it as a filter on the classify panel. So where you would choose your classifier, you could choose this filtered classifier, meta classifier first. You would drop your classifier in as the base classifier. you would then choose this discretization filter, and then you see below it the widget for the discretization filter, and basically what you need to do is tell it which ones of your attributes that it should discretize, and so then it will do that, and then you can use them in your model. Okay, so that's discretization and how you can use it in Weka. And of course, there's so if you wanted to probe more into the parameter values, a lot of which are just shortcuts for being able to list the number of the set of features to discretize. There's also things that you can manipulate about the representation of the resulting features, whether they will be the set of binary features or whether they will be single nominal features with a set of values. Those are options. You can look at the documentation for that. So the final thing we're going to talk about today are time series transforms. This example that I'm going to use for time series transforms actually came from a project that a student did in my class several years ago. That student was doing a smart home project where what they were doing is using sensors to monitor air quality. And so in the case of air quality might be related to how many people are in a room. And so to collect their data, they had their sensors. The sensors made readings every so often. And they also sometimes had somebody sitting in the room to count how many people came in and how many people left. So at various time points, they had number of people in the room, and they also had the CO2 reading from the sensors. Now, there's a problem because when people enter the room, they immediately start to affect the air quality. However, it takes a while for the CO2 that they're breathing out to dissipate throughout the room and be noticed by the sensors. So the effect of people coming into the room is going to be felt later than when those people actually entered the room. So in that case, what we have to do is take the data that's time-stamped. We need to shift the observation of number of people forward in time so that the observation of number of people aligns with the sensor readings that are relevant for that number of people. So in order to do this, we can use time series transform widgets inside of Weka. They're filters. They're filters that create new features from the features that you started out with. Well, actually, what they do, they don't create new features. Actually, what's really important is that what you need to do is copy your features so that you create new features, and then you use these transforms to manipulate the values. Now, something to note about how values are manipulated when you do a time series transform. What will happen, so you'll see there are two kinds of transforms, one of which just shifts values and the other of which looks at the difference in values and then records that difference. Let's start with the simple case where you just shift. So the rectangle at the top of this slide, where we have the yellow marked, shows the data in its original form, where you've got the number of people observed at a time point, and you've got the CO2 reading at that time point. But we already said why it is that that's misaligned. So what we really want to do is shift the observation of number of people down 2 time notches. So below that, you see what happens after the shift takes place. So the number of people observed at time point 1 is now at time point 3. The number of people observed at time point 2 is now in time point 4. So, and they're correctly aligned with the relevant CO2 readings. But what happens to the first 2? Because there wasn't something before time point 1. So what happens is in the top 2 instances, now there's an unknown value for number of people. And that's okay. You can either leave them as question marks or you can remove those instances. And you'll see that Weka allows for both options. So here are the widgets. We see two different possible time series transforms. There's time series delta, where what you keep is the difference between a feature value and one that's either before or after it in the list, and time series translate, where you actually move the value down. In all cases, you have to say which attribute you're talking about. So attribute indices is which attribute are you going to manipulate. And as I said on the previous slide, what it's going to do is overwrite these features. So what you want to do before you do this is copy those features so that you can apply the transform to the copy and you can keep the original. So that's why the first option in both of these cases is attribute indices. Underneath that is fill with missing. So fill with missing is if you have, say, some number of instances that will be left without a value because, let's say you're shifting down 2, and so the first 2 are going to be not have a value, or if you're shifting up 2, then the last 2 in your data set are not going to have a value. Fill with missing says that for those instances, you're going to have a question mark. If fill with missing is false, what you'll do is remove those instances. So you'll notice that you have fewer instances after you do the transform than you had before. Instance range is how many instances before or after you should look. And so -1 means you look back 1. +1 means you look forward 1. And you can look back 2, you can look forward 2, etc. Then finally, invert selection refers to the set of attribute indices. And so what happens is, let's say you want to do the transform on, you have like 50 attributes and you want to do it on 48 of them. You don't want to list all 48. So you might list the 2 in attribute indices that you don't want to do the transform on, and then make invert selection true. And then what it will do is pick the 48 that you didn't list. And so that allows you just a kind of shorthand. So now we're at the end of our discussion for today. And feel free to listen to this multiple times if you need to. You can also manipulate the speed if it's too fast. If you have questions, you can post them to Piazza. Remember that you can come to the lecture time and ask the TA who will be there to answer your questions. And I will be back on the 26th to give my lecture on that day. And I will also have office hours after class on that day. So I will see you then, and I hope you're having a great week.